crowd. Thank you all for coming to this session. So today we're going to be talking about deep learning with TensorFlow and Keras. So some administrative stuff. Later on in this session, you're going to need to go to this link to connect to your RStudio server instance. And right now it's not going to work yet because we've had quite a few more people than we expected. So we're still in the process of spinning up the instances. But we won't need to go there right now. So we can come back to this a little later. But hang on to the stickers if you, if you put it on your laptop, you want to keep the number in the back so you know what number you're assigned to. So the schedule for today.
Can you maybe briefly go back to the first slide so we can note down the URL?
Oh, I mean, we'll go back to that. We'll go back to that. Yeah. Thanks. So we're going to be in here for about an hour and a half, give or take, and then we'll get some drinks, coffee. I don't know what they serve here, but hopefully it's good. And then we'll come back for some more, maybe. So let me tell a little story. So I was getting some dinner with friends last night, and then about 3 drinks in, guy sitting next to me, Dave, you in here? So Dave was like, hey Kevin, so when's your tutorial? I was like, oh yeah, Wednesday afternoon, like yeah, all day tomorrow, I'm all good. And then he was like, Wednesday afternoon is when the conference starts, and then I was like, all right, this guy's gonna be fucking with me. So I put on my phone, and then I was like, oh, okay. All right, so the good news is that all the content, it's mostly there. I didn't do any timing runs, so I don't actually know how much content we have, but I think we're gonna be okay. So even if we finish early, it's pretty nice outside. We could grab a drink or something, take a stroll by the river, all that. And then afterwards, the locals. Who's local? Yeah, you guys can show us around. Yeah, that's right. All right, so these workshops, they have some educational objectives, and these are hours that they're going to be there. So by the end of the session, you should be able to describe what neural networks are, be able to name some software packages, and then maybe actually build some neural networks. So the overarching goal here is not to make you an expert in deep learning. You can't do that in 3 hours. And but you should be able to just learn enough to basically impress people. But why would you ever want to do that, right? It's dumb, but it's okay. It's okay. We're still gonna get you there. So why do you care about this stuff? Why might you care about this stuff? So who's in academia? Who's an academic? All right. So whatever you're working on, just change the current technique to like blah blah with like deep learning, and hopefully you'll get more funding and then get a paper published. I don't know if that works, but give a shot and let me know. And then if you're in like consulting or something like that, this actually works, okay? So you go tell your client, okay, we're doing this thing this way, but now we're gonna deal with deep learning AI. And man, just rake it in, just rake it in. Is this being recorded? Oh, okay, all right. So keeping in mind that we have, maybe 3 hours. So we want to hit a diverse range of topics because everyone works on different types of problems with different types of data. So instead of going into the theory too much, we're gonna try to get you exposure to working with different types of data. And the idea is that when you actually work on a problem at work or for your research, you're going to see a problem and then you'll know, okay, I've heard of like this type of neural net before, and then maybe that's worth a try. So you know where to go back to and then study more on a specific subject. And then that's sort of the theme. All right, so let's talk about deep learning. Some water for that. So deep learning really is just a rebranding of neural networks. It sounds cool, but it's just neural nets. And then it's It's just a machine learning technique. So machine learning used to sound pretty cool, 5 years ago, and now it's just okay. But it's basically a way to learn a function or some black box that takes some inputs and makes some predictions. Okay, so right. Took a little while to render, but there it is. So this is like as much math as we're going to do today. So if we have some inputs x, we want to predict y, and then we want to come up with some function x to do so. All right, and then this is like probably not the most general way to think about it, but this covers a lot of problems. And for neural networks, at least the vanilla feed-forward neural nets, you can think of f here as just a composition of functions. And then these functions are parameterized by some weights. Okay, so this is really a parametric model. And then for the most part, these functions are really simple. You can think of them as basically matrix multiplication. Okay, so then if you can put your inputs into like one big like matrix or big vector, and you're successively applying linear transformations to them, and then these linear transformations will need to be followed by some sort of non-linearity, and then usually there's some sort of thresholding, and then it's gonna be more clear. But if you think about it, the reason why we need the non-linearity is that if you just compose a bunch of linear transformations together, you're just going to be doing like one linear transformation, right? So that's not going to be very useful. So we're going to go over some pictorial representations of deep learning, and then disclaimer: most of the stuff in here is like ripped off from other presentations by other people in different books, which is all good. And so here's one picture. So you got an input layer, and then you have some hidden layers with nodes, and then these nodes again are sort of parameterized by some weights, and eventually these transformations will give you some output. So here's another picture. So it's kind of similar. You got some inputs, and then you have these weights, and then you're multiplying the inputs by the weights. You're sort of adding some stuff. So the green stuff is like the linear transformation, and then you got the pink stuff, which is your non-linearity. And then here's one where the input is an image, and then you're sort of distilling the input multiple times in order to get at the final output. So every layer will output something that's more and more useful to help you make the final prediction, which is the output. It's like making wine or making vodka. You got some grapes, and then you're mushing them up, fermenting them, and eventually you get something that's drinkable. So here's another picture. So you got inputs going through different layers. The layers are parameterized by weights again, and then eventually you get some predictions. So in the beginning, these weights are going to be they're randomized. So they're going to be kind of crappy. They'll give you some crappy predictions. And then you need to tell your neural network, the training algorithm, how unhappy you are, basically with each prediction that it gives you. So in the regression case, your loss function might be your mean square error, right? So you need a way to quantify how bad these predictions are, and then once you have that, you can feed it back to the optimizer, and then the optimizer will take a look at how unhappy you are, and then try to make you happier by sort of tuning the knobs on these weights a little bit. And then the idea is that you do this over and over again until the weights are such that you get some inputs and then you have some outputs that make you happy. Okay, so in terms of software, we're gonna focus on TensorFlow and Keras for this session. There's a bunch of other things out there. PyTorch is probably the next most popular ecosystem. There's a CNTK, which is I believe less developed now, and MXNet, which there's a lot of effort by Amazon to making that better, and a few others. So TensorFlow is really a general purpose computing library. You don't have to do deep learning with it. There's examples where people have built on TensorFlow to do things like to fit like Bayesian MCMC models, but it can be used for deep learning, and then that's I think where most of the use cases are today. And Keras is just a high-level API on top of TensorFlow and some other backends to make it easier for the user to build and train neural network models. So here's a little picture that shows the popularity of these frameworks in academic papers. And now we can talk a little more about some technical details. I'll pause there for now. Any questions so far? Am I making sense? Yes.
The link to the slides, please?
Oh yes, the link to the slides. They were on the title page, but we're gonna go back to that, and then you can all take pictures and know that. But everything's gonna be open source, including the code for the demo that we're gonna do. But yes, that will be made available. Anything else? Yes. Yeah, Theano, I believe was they announced that they were gonna stop developing it maybe like a year ago, or maybe somewhere. Is that right? Yeah, something like that. But today, basically, everyone's using either TensorFlow or PyTorch. So a little more context. So TensorFlow is mostly worked on by Google, and PyTorch by Facebook, and MXNet by Amazon. So most of these frameworks have quite a bit of backing behind them. All right. Okay, so since we're talking about TensorFlow, we should talk about tensors. So tensors are basically multi-dimensional arrays. You can think of them as generalized vectors or matrices. I don't think it has that much to do with the tensors you see in like physics class, but just think of them as sort of the data that you're going to be working with. And so here are some examples of tensors, and then we'll refer back to this as we build some models. So basically, one of the most tricky parts in doing deep learning is getting your data into the correct format, and then by correct format, I mean just getting the dimensions of your arrays right. So recall that we have this this graph of computations. You can think of this process of evaluating your predictions and then feeding into the optimizer and tuning the weights as sort of this computation graph, and then your tensors are flowing through that computation graph, and that's why it's called TensorFlow. So here's a really cool picture of that happening. All right, so I hope I've bought enough time for the instances to be spun up. So let's go back to this link. And then once you're in there, you can put in.
AWS ran out of GPU instances.
Do our stickers, are they stickers that we have there under 91? Not under 91. Yeah, just in case we find out. All right, latest update from your captain. So AWS ran out of GPU instances. So they kept us at a 91 extra sticker. You can grab one from the back, and we're trying to see if we can get at least CPU instances. Has anyone successfully logged in? And okay. Okay, let's give it a minute to see how we're going to resolve this. And then I just realized that I have a 95. Oh, you got 88? Okay. Thank you. Oh, yeah, let me do that, sorry. Where is that? All right, who has not been able to log into an instance? And then, so keep your hands raised. Out of you guys, who has a number less than 91? Okay, that's interesting.
It says the capacity is reached on the Colorado server.
Yeah, we can't get it.
Oh, so it's a Shiny app that's bugging out.
Yeah.
Oh, okay. All right, that's easily fixable. Sorry, guys. This is definitely a larger crowd than we expected.
Yeah.
And I thought Shiny was supposed to be scalable, yeah? Yeah.
This is not your
We're gonna give it like one more minute, and then if we don't make an improvement here, we can do a plan B. And I don't know what plan B is. This seems to work now. Okay.
slide from the first URL.
Oh, okay.
Thank you.
Does everyone else got the link for the Shiny app? All right, the Shiny app should have been fixed. So if you weren't able to log on, please try it now. And then we'll do a status check in like 30 seconds. If you have a number that's over 91, please raise your hand so I can do a quick count. All right. All right, so now if you have 91 or under and you are not able to log on, raise your hand. And then what errors are you getting? Just shout it out.
That one that gateway, what do we have over here?
So we have a 502, 503. And if the app isn't working for you, please refresh and then try. And then we'll Is the font okay for those in the back? Should I make it bigger? Good. All right, so I think what we can do right now, let me just get an ETA on this. Okay, so the CPU instances should be up within the next minute. So let's wait for that so we can get everyone on the same page. And for those of you that couldn't wait and then try running stuff, is everything okay? Yeah. Okay. Thanks. Okay, so it looks like it's taking a little longer. So what we're gonna do is we're gonna go through this first notebook. So sorry for the folks that are over 91. Oh, I mean number over 91. But we can we'll just go over this notebook and then maybe even halfway through we can get you guys on. So okay, so the first example is like the classic example for neural nets, and it's basically trying to classify some handwritten digits. So we're working with some image data. So who here actually works with image data? Oh, that's surprising. There's a few of you, because I never do, and I'm like, this stuff is pretty worthless to me, but I'm gonna do anyway because this is what everyone does. But it's okay. Maybe we'll all be like, working on self-driving cars soon. So we have this data set, and then you can get to it. It's a built-in Keras data set, so you can just call this data set evidence function. And then you see that this thing is basically a nested list. So the first element of this list is trend, and then it contains some x values and some y values. So the x values in this case, we basically have 60,000 28 by 28 images. So you can think of these as 60,000 matrices. And these matrices basically represent the pixel value. So these are grayscale, so we just have one channel. So then they represent, I guess, the intensity of a pixel, if you want to think about it that way. And then the y is just 60,000 numbers. So for each of the 28 by 28 images, you will have a number associated with it that's the actual number that's on the image. And then so we have a training set, and then we have a test set. And Kelly, you're here? Can you just monitor the chat, and then once we have the CPU instances up, we can get it on there.
Okay. Do you want him to spawn up the cloud instance? See if we can get everything on cloud as well?
Like our studio.cloud?
Yeah.
That's not gonna work.
Yeah.
Yeah, because those are 1 gig of RAM. So just get the EC2 instance. We can wait a little bit. Okay, so we see that. Yeah, so we have that, and then now we want to visualize this a little bit. So we have a little helper function here. So if you think about it, if you take this thing right here, so this is taking the training data, and then we're taking the x's out of the training data, and then let's say we take the first element. What does that look like? So that's our 28 by 28 image, and then you see that there's some numbers associated with each pixel. So there's a function as raster that can convert this into something that can be plotted. So if we run this, then we see that the first example looks kind of like a 5, and then the second example looks like an 8. So to the neural network, everything is just numbers, but we can sort of interpret the data by plotting them. All right, so in this next block, what we're going to do is we're going to use this, this operator. It's from the Zealot package. It's been re-exported by Keras. And then what it does is it's able to unpack nested lists like the one we have up here. So this is a syntax. You have basically a vector of symbols, and then you're saying that the first list, we want to unpack it to xtrand and ytrand, and the second list we want to unpack to xtest and ytest. So alternatively, you can also do something like, you can subset this MNIST thin and then assign, like have 4 separate lines to assign them. But this is just a quick way to do it. And then what we're going to do for this first example is we're going to collapse each of these images into one really long vector. So if you think about it, the image is 28 by 28, and then we can represent that data by basically taking each pixel and then just putting them into one vector. So that's what we're doing here. And then if you remember that little, wonder if we can get to it. The tensors table that tells you what they should look like. So basically your first dimension is always samples. And in this case, samples is basically how many samples you have. So the number of rows in xtrand is how many images you have. That's your samples dimension. And then the second one is basically how big these vectors are. And then we want to convert these into the 0, 1 range. So when you're working with neural nets, your input values, you want to normalize them to be in the same neighborhood in a sense. You don't want to have like some values are really big, some values are really small. And then the standard way is to get them into like 0 to 1 or like -1 to 1. Okay, so then we also want to one-hot encode the classes. So there's a helper function from Keras that does that. It's called toCategorical. So then you basically pass to it your labels and then the number of classes. So we see that now the dimension of xtrand is the number of samples by the size of our vectors, and then the ytrand are going to be we should take a look at this. So basically now each y label has been converted to a vector where there's a 1 corresponding to the label and then 0 elsewhere. Okay, does that make sense so far? Yeah. Okay, so now let's define our model. So there's 2 different APIs in Keras for defining models. There's the sequential model API, and there's the functional API. So if your neural network is straightforward in the sense that you're taking some input data and then applying one transformation after another to that input data, you can use the sequential API. And if you want to do something that's more complicated, you can basically have arbitrary graphs of computations. But for this example, we're going to use a sequential API. So we have our sequential model, and then what this is doing is layer dense as a fully connected layer. And then basically the input shape specifies how big your input is, and we know that, right? It's 28 squared. And then what is this doing is taking the input layer and then connecting it to the dense layer of 256 nodes, and then 128, and then eventually we have our output layer, which has to be which has to have 10 units because our one-hot encoded label vectors are of that size. And so the activations here, this is the nonlinearity that we talked about. And for most applications, you can start with ReLU. Basically, what it is if the value after the linear transformation is less than is negative, then we just replace it with 0. That's all it does. Okay, so let's see. And note that we're not assigning this result to anything, and that's because in the Python API, these objects are modified in place, so that carries over to here. So it may take a little bit of getting used to, but as soon as you code layer dense on this thing, you've already modified the model object. So that's something to keep in mind.
CPU instances are good to go. So if you have a number 92 or above, try to assign it again, see what you get.
And just for the recording, right now we're getting everyone else that didn't have an instance and instance. Okay, so one question is, what should this architecture look like? So if you've worked with other machine learning algorithms, for example, let's talk about like random forest. You might have to pick your sampling rate, sampling the columns, and sampling the rows, and different hyperparameters. So this is kind of like that. So it's hard to say what architecture is going to work for you for your specific problem. So what people usually do is just to just start somewhere, and then get it to start training, and then you can make it more complex if you think you're underfitting, and then once you start overfitting, you can start doing some regularization techniques. So I think I ran that. And then once we have our model structure in place, we can compile it, and then that's basically telling it what optimizer we're going to use and then what loss function we're going to use. So again, the loss function is it tells the machine like how unhappy we are with the different predictions. And in this case, we're using categorical cross entropy is a pretty standard way of pretty standard loss function for multi-class classification algorithms. And then the optimizer, again, these are there's ongoing research on which types of optimizers work well for what types of problems. And then if you're just starting out, add-in is one thing that's really popular. So basically use that, and then if you want to really dig into what these things are doing, you can read a paper. And if you're working on your problem and then you're not getting good results, then that's like one thing that you can look at among a bunch of other things. And then as we're going through these examples, I think we'll get a better feel of how to make these things work better. The folks on CPU instances, were you able to log in? Yep. All right, so if you're running these things, you see these units here? You want to make them like a lot smaller. Because so these take a few seconds I think to run on a GPU, and if you're on a CPU instance, basically you want to make your model smaller by like an order of magnitude. Okay, so let's see. So we compile the model, and then now that we have a compiled model, we can try to fit this model. So one thing that that you have to specify is the batch size, and then that's basically for each parameter update that you do. So remember that graph where we're feeding the loss back to the optimizer, and then we're tuning all the weights a little bit. So in deep learning, most of the time you're not putting like all of your data in at once. You're taking a sample of the data, feeding it through. So usually you might put in 32 samples or 64 samples. In this case, we're taking 128. And basically each epoch, so a little bit of definition here, each epoch is basically one full pass through the data. So if you have a sample of like 100, and then your batch size is like 10, then each epoch is going to contain like 10 parameter updates, because each time you're feeding 10 samples. And as you look at this neural network code on blogs and stuff, you'll notice that the number of units tend to be like a power of 2. There's really no good reason for that, I don't think, other than convention. And if you put something there that's not a power of 2, people will be like, do you know what you're doing? So even though it doesn't make that much difference. The batch size, I think, does though. So it has something to do with like the architecture of GPU. So for a batch size, you usually want to pick a power of 2. So the way we fit a model is, again, so this thing right here, if we were to just run that, it's going to fit the model in place and then modify the model object in place. But the fit function also returns a history. So that's why we're assigning to this symbol here, which we can inspect in a little bit. And then the fit function also has a validation split argument that you can utilize to basically split your data. So in this case, well, we're using like 80% to do the training and then validating on the 20%. You can also specify explicitly, if you did this beforehand, what you want your validation set to be. So if you run this, hopefully this doesn't crap out on me. Yes.
Why this time you have assigned the model history? Because previously you didn't assign to anything, you just used the files.
Right. So the fit function actually returns it has a side effect of modifying model in place. So the first argument is model, so it's going to modify model in place, but it also it has a return value, and then that return value gives you information on the training history of the yes. Yes. So the question was if you want to train a model and then save the weights of the model and then pick it up again later. Yeah, there's a way to do that. I actually don't know off the top of my head, but there's a function that you call on the model object itself. So you don't necessarily have to assign this model to something else. Does that make sense?
Yeah.
Okay. I think another question? Yes.
I noticed your graph was dynamic with the training, but you're not actually plotting anything in the graph. Because that's kind of a bit of magic in our studio that makes that happen.
Yeah. So at each, I actually didn't pay attention, but you're talking about this, right?
Yeah.
Okay. So the question for the record was basically this thing was plotting as the model was training. How does that happen? I think it's some like our studio magic. But basically the idea there is that if you define a model and then it starts training, and then you see that your loss isn't going down and it's taking a while, right? Then you can maybe stop early without having to wait for however many epochs you specified. So that's a way to sort of save you time as you're iterating through your model. What time is break, by the way? When? 3? Okay. All right. So once this model has been trained, we can use the evaluate function to so we're passing the test data set here, and then we have some some metrics. But it will be interesting to see if we can actually plot some things from X test and then compare it to Y test. All right, so I don't usually subject people to like writing a bunch of code in these tutorials, but let's try this right now. Give it a shot. See if you can plot, say, the first 3 or 4 images of X test and then compare it to Y test. And is everyone online now with our Studio Server instance? Okay. Okay, has anyone done it? I actually don't know. Like, I never tried this before, so this is like real life coding. It works? What did you have to do?
Just updated your function you had before with an argument to specify whether to get the training or the test.
Oh, so you're using the helper function from?
Yeah.
Would that work? Let's see. Where was that? This one right here?
Yeah.
And then you just do test. Okay. Let me code this out. Example 2. All right. So, and then we can check, say, this one. Okay. I actually didn't expect that to work because I thought we modified the X trend and the X test and Y test in place, but this is pretty cool. All right, so we see that we've made some decent predictions. And the folks on the CPU instances, were you able to run the models? Can I get a thumbs up? Okay. All right, so let's go on to the next one. Actually, any questions on that last notebook? Are we okay? Oh, okay. All right. Oh, yeah. So the only difference is we changed the trend to test, as that gentleman pointed out.
I think you need to use a model to predict the test. The counter label, we have to compare with the y test. Otherwise, why we need the model?
Oh yeah. Okay. That was dumb. That was definitely my bad. So the question or the comment was that I put a test there, so that's completely worthless. So, all right. So let's try this. So maybe we have like awful predictions now. We'll see. So is that right? So this will be the trend. Hold on. No. Hold on. No, I think that was okay because we're talking about x's and y's, right?
Where's the model like prediction?
Yes.
Where do you evaluate it?
It's a model.
Oh.
Predict the class.
Okay. Yeah. You're right. That's a good catch. That was almost embarrassing. Okay. So I'll let you finish off because I think you'd give me like half the answer and then not the rest of it. So how did you get the predictions?
I haven't gone through that yet. I thought you were asking to like have something to compare to.
Oh, okay. All right. All right. Predict classes. And then what do I need to put in there?
X test.
I need to put in X test.
That's it.
That's it?
Oh, we need to, just the first one.
Yeah, that's what we did last thing, but that's
So
The first value of one, open bracket,
first
one is
example.
X test, and then the first one.
yeah, comma. Deuce has got one. Get rid of one of those columns.
If you run it without the one comma, you get output from 0 to 9.
Say that again.
So just replace what you've got highlighted just with X test.
With X test.
Yeah, and that'll give you all.
Ah, this works.
So you can do it that way.
So then this one should give me the first prediction. Is that right? So then, so we don't care about that. So this function is still okay? And then we can look at the first one. All right. Let's try number 60. All right. So this is a real deal, right? I'm not cheating you like I was doing like 5 minutes ago. All right. All right, so I think someone commented that maybe we want to get this into Git to make the predictions. We can use predict classes. Oh. Okay, and then I'll push this change after the session. Yes, question.
Yeah, or how do you get rather like I assume it was scored. So when number 1 is 7, I assume it's something that says it's 95% probability 7. Is that what's happening in my understanding?
You're.
Can you get a rating for that prediction in some way?
Can I get a what for that prediction?
So like a level of confidence.
Oh, I see. All right. So the question was, can you have some sort of confidence interval or like prediction interval or credibility interval, whatever, right? So some sort of uncertainty measure around your predictions. So I think right here we can't do that given the way we've set it up, but there is some research around like Bayesian networks that I think can take that into account, and then another.
So maybe another way to ask this question is, can we get the level below the softmax? Right, the softmax is taking the probabilities across all the digits, and so the question is, can we access that layer instead of the actual prediction of the softmax?
Oh, I see what you're saying. Okay. So you want basically the raw probabilities instead of just the predictions, right? Would predict give you that? Prob? All right.
You need an extra
Yes, you can there.
What do I need to give it? Or is this okay? Let's try that. So is that what you were looking for?
Yeah, that's fine.
Let's see. So this thing is still gonna give you that. So hold on. Predictions prob.
You should be dimensions by 10.
Yeah.
So each row.
Yeah. Okay. Yep. So I guess like what predict classes does is basically getting the argmax of that vector. All right, learning something new every day. Okay, do we have any anything else on this example? Okay, so let's move on to the next one. And this one's really similar. It's going to be the same problem, but we're going to attack it a little differently. So let's clear our workspace and then start over, because each of these notebooks is independent of the other ones. So in the first example, what we did with the images was sort of collapse them into one-dimensional vectors. And for this exercise, what we're going to do is we're going to maintain the spatial structure of the images. So what we're going to do is, by the way, if you're the type that likes to code up your own thing, like during tutorials, feel free to do something like this and then start coding. But for me, I'm like can be arsed. Is that what we're gonna say around here? All right. So what we're doing here is basically everything's the same, except now when we reshape the images, we're going to put it into this type of structure right here. So the first dimension, again, is the samples, like it always is. And then now we have the number of rows by the number of columns. And then the last dimension here will be how many channels you have. So when you're working with image data, it's the color images, you have a red, a green, and a blue channel. But in this case, we have grayscale, and that's why this last dimension here is just 1. And then our input shape this time around is not just one lone vector. Right now, it's basically a matrix, and then the depth of this image is 1 again because we have grayscale. So these should be familiar. And then now we're going to define a convolutional neural network. So CNNs or convnets are basically the go-to nowadays when you want to work with image data. And before we actually run this, we can talk a little bit about what these convolution layers are doing. So instead of copy and pasting some images from other slides that other people have built, I'm just going to go to the actual slides. All right. And I probably should have saved this locally just in case their server's down or something, but we're good. All right, so what we were doing before, okay? So we had, in our first notebook, what we did was we basically stretched our image into one lone vector, and then we multiply by some weights, our linear transformations, and then we end up with the output. And then what we do with the convolution layer is basically we want to again maintain that structure. And then the concept here to introduce is this filter thing. So what this filter is, I wish I could figure out how to make this side by side, but so for example, our kernel size here is 3 by 3, and so here we got a 5 by 5 filter. But you can think of a filter as sliding over that whole image, okay? And then the filter in our case is going to be 3 by 3 by 1 because our image only has one channel. So what we're going to do is we're going to slide this filter over our image that was 28 by 28, and then at each at each location on that image, we're going to take the dot product of the values of the image locally against our filter. Okay, so if you think about this, going back to the code here, what we're doing is we have a 3x3 thin square that's say at the top left of our image, and then that's basically 9 numbers, right? The filter is also parameterized by weights, so we have 9 numbers there, and then on the image there's also 9 numbers. So then we're basically just taking the dot product of those two things. So, and then what we're doing is we're doing that across the entire image, and eventually we end up with an output that looks something like this thing on the right. So this is slightly abstract. So first note that the dimension of the output is going to be smaller than the dimension of your input image. Okay, try to convince yourself of that, because so let's think of a more trivial example. So let's say we have if we have a 5x5 image, okay, and then our filter is 3x3, then if we are just talking about the top left, okay, our filter is on the top left, so the first dot product is going to give us a number, the second dot product is going to give us a number, and then the third dot product, and by the time we take the third dot product, we are at the top right corner of our 5x5 image. I wish I had the board. Does that make sense? Yeah? So basically that's why if you don't do any padding, the convolution is going to give you an output whose dimensions are going to be a little bit smaller. Okay? And then the other argument that we pass to our layer conv2d function is the number of filters. So each filter is going to give you one of these. So depending on the number of filters you have, you just end up with some value. All right. So we started with an image that's kind of flat. You know, if you're working with color, then it has a little bit of thickness, and then a convolution layer, depending on the number of filters you have, is going to give you some value. And then usually in this type of networks, your input comes in, and then at each successive layer, you have something that's sort of smaller in the spatial dimension, but it's getting thicker, if that makes sense. Okay, so here are some pretty pictures. Oh, okay, so okay, this is a great deck. So here we have a 7x7 input. This is, you know, I wish I had a board. So we're sliding this 3x3 filter across this thing, and then, you know, you do that, and then you end up with the output value. And then if you think about it, if you keep adding these layers into your network, if we do this, 20 times or something, and sometimes these networks get really deep, you end up with something that's so skinny and long that you can't really take convolution layers anymore, and then that's why sometimes you want to like pad your at each stage you can pad the input, the output from the previous layer, so that when you do the convolution, you end up with something that's the same dimension. So these are, a bunch of different tricks you can use to try to tune your neural network. So this is like one thing that that might take a bit of getting used to if you're just used to tuning GBMs or something. That there's like there's just only so many things you can do, and then you can just run a big research and then call it a day. But then with neural nets, it's slightly more interesting. So you can totally knock yourself out doing some of these things. So in this particular model, and then feel free to change some of these. Just know that if you make these really big, it's gonna run for a while. But you can always hit the stop button and then redefine it if you think it's taking unreasonably long. So here we have a couple of convolution layers, and then in the second convolution layer, we also have a strides argument, and then that basically tells you when you're sliding the filters, how much you want to slide it by. So by default, you think about it, you're taking a stride, you're going like 1 pixel over, and then you can take 2 pixels over, or as many pixels over as you want. But usually you want to stick with some small number, and it's also you also want to take into account how big your filter is. Okay, so we also have a max pooling layer in here, and then you can think of this like almost as a convolution, except the little filters that go around, you're actually just taking the maximum number in the filter and then outputting that. And then I wonder if there's a. All right, here we go. So here's an example of that. So you got a 2x2 filter with a stride of 2. So basically, over here you're going to take the maximal element, and then here you're going to take the maximal element. So pooling also sort of downsamples your image. So you may be thinking, all right, so if I were to work on an image recognition problem, like what the hell do I use, right? So again, the answer is, sort of look at what people have been doing, look at the latest papers, see what the trend is, and I think if you follow the research, you see that results are getting better and better, and then so you want to see what's been working well recently, so you can use that to inform your starting point in terms of your architecture search. And I guess eventually we won't have to do that because that will be automated. Okay, and any questions about some of these so far? So I just went through a bunch of like potential building blocks that you can use. Should we go over some things again, or are we all good? Yeah? Okay, so the next steps are pretty much the same. We got some training that we gotta do. Did this take a while? Or not too bad, yeah? Oh man, that's taking a while. If you're who successfully ran this on a CPU? Right, the guy in the back. What filter size did you use?
Just the stealth standard. Takes about half a minute.
Oh, so you didn't change anything? Okay, all right. Yeah, I guess this is a good time to talk about if you were actually working on neural nets, what hardware you should be using. So if you have a laptop or a computer with like an NVIDIA GPU, you can use that. But if you're on a MacBook, which I think a lot of you are, you can't really do that. So there's a bunch of cloud-based services that you can try. So all of the public cloud vendors have GPU instances, and then there's also a service called Paperspace that focuses on these types of instances. And then I think basically for all of them, there are images that you can use where it will just have RStudio set up for you with the necessary packages. So those things, are worth trying out. And if you're in a university, I'm sure there's something that in like neighboring departments that you can borrow, or you can try to get funding to buy some crazy GPU machines. Anyway, so it looks like it's done training, and then we can evaluate our little model here. Okay, so is this accuracy better than what we had before? It's a little bit better. I mean that. So when you're interpreting these things, it's kind of tough without a real problem, because a 1% difference in accuracy could mean millions of dollars, or like a bunch of lives lost or saved. So, but in this case, we don't really care. But keep that in mind. Okay, so I think that wraps up the image stuff that we're gonna talk about today, and I think we're actually right on time in terms of our schedule. So we're about 5 minutes from break, so I don't think it makes sense to jump into the next notebook right now. So do we have any questions on yes?
Sorry if you've explained this before, but what is test loss?
Test loss is the loss on the test data set. So I think we defined the loss to be like categorical cross entropy. It's just some measure that tells you like how off you are in terms of your predictions. So classification problems are a little trickier to interpret, but you can think of this loss like analogously in a regression context. That this could be something like mean square error, right? Like how off you are from your predictions. So this is really just a function of the predictions that come out of feeding X test to your model, and then comparing that against the actual labels.
How does it compare to precision and recall? You know what I mean? Like,
yeah. So in this case, we have like I think you might be able to put precision and recall in the, what is it, as a metric, because like it's just a different way to look at how you're doing. I want to say it's in there somewhere, but I'm not quite sure. All right, if there are no questions, let's go on break, and then I think we come back in half an hour, so around 3.